Saxon Advanced Mathematics, Lesson 79. Greetings, students. Our lesson today isn't horribly difficult in terms of calculations. It can be a little bit confusing because we can lose ourselves in the details of the process without realizing what we're doing. So I'm going to spend a little bit of time trying to help you wrap your head around what the heck it is we're trying to do and why we would want to do it. But just rest assured right now that the actual mathematics, the calculation steps, they're pretty easy. There's not anything very difficult about them. All right, what we are talking about today is, and I've got the first topic there, but let me start with something easier. Complex numbers. Okay, we know that complex numbers arise when we have something like square root of 4, right? And you can't, oh no, I'm sorry, the minus sign would need to be in there. Right, not like that. The minus sign is inside the pig house. There's no such thing as two numbers that multiply to minus 4. So we instead rewrite this as 4 times minus 1. Then we turn this into the letter I, and we would call that 2i, right? That's what imaginary numbers come from, is this whole problem of having negative signs in the pig houses. And it's just not allowed to happen, right? We learned that there's a thing called complex numbers. Like I said, these are the imaginary numbers. This is the real component, and this is the imaginary part, right? That we can have this combination of the two, and we call that a plus bi. And what we've recently learned is that we can graph these. We can graph these in this format, and we just graph them as rectangular coordinates. We keep it really simple, coordinates. We put the real number on the x-axis, and we put the imaginary part on the y-axis. Super simple, nothing dramatic about it. We just label our axes accordingly, and we're good to go, right? And that's fine. That's easy. That's the rectangular coordinate of a complex number. But we learned that we can also have complex numbers as polar coordinates. Okay, so we can graph them as rectangular coordinates, but just as with regular numbers, we can move between rectangular coordinates and polar coordinates. We can do the same thing with complex numbers. It works exactly the same. The process of moving from rectangular to polar, back to rectangular, whatever you need to do, it's the very same process. We use our triangles. We use sine and cosine to move in one direction, and we use tangent and the Pythagorean theorem to move in the other direction, right? We've been doing that since Algebra 2. We knew how to do it by this point last year. So we can move back and forth from rectangular to polar. The only thing that's weird about that is that when we write the polar form of a complex number, it looks a little different. And let me give you an example. This is the way we write, I'm going to call a normal polar form. We've got an angle and we've got a hypotenuse. Right? Sometimes we call this a direction and a distance. And sometimes this relates to These words are a little too close together. Those relate to that. Sometimes the hypotenuse will also be called the absolute value. And I don't want to say too much about that because I don't want to confuse you. Just suffice to say that it's not really positive or negative. It's always just a generic number. It doesn't really carry a sign. So sometimes you'll see that expression used. Don't let that freak you out. Just know, oh yeah, absolute value, that's the hypotenuse. I find hypotenuse and angle to be the most useful names for these because they help me visualize the triangle, right? When I talk about the angle and the hypotenuse. Now, here's the problem. If we use this same sort of symbolism, the same organizing technique for our complex numbers when we were writing them as polar coordinates, then we would confuse them with the quote-unquote normal kind, the vector form, if you will. So when we use complex numbers in polar form, we just mix it up a little bit. We use a different strategy, and I'm going to write this same angle. It's already in polar form. It's not like we're changing it back into rectangular. We're just using a different set of symbols. We write it like this: 4 cis 30 degrees. 4 represents the hypotenuse, and 30 represents the angle. We could use any of these other words to describe these, but I'm just going with my go-to favorites, okay? So instead of this little box thingy, we just write this. This stands for cosine plus I times the sine of. We'll talk a little bit later. That's really instructions for how to change this into rectangular. So that's easy. Don't let that freak you out. Just know that, again, these two mean the exact same thing. This is just, we write it differently when we're dealing with complex numbers because that way we can tell the difference. Okay? When they're in rectangular coordinates, we can tell the difference because complex numbers have an I. There's no I in this format, so that's not going to help us tell the difference. All right? So don't let this CIS thing freak you out. Just go, oh, it's a polar coordinate, and I can treat it exactly like it is one. Okay, now, we're still going to talk about this Demois guy, who, P.S., was a French refugee, I believe. Let me just double check what John said. Yeah, he lived in London in the late 1600s and the early 1700s. He was a French refugee, and he lived in London, and he was into doing cool math stuff. So what he was interested in doing was taking like a generic form of a complex number expressed as a polar coordinate, and what he did was he called it R plus, no, I'm sorry, not plus. Okay, so here we have, this is a C. So this is the polar form of a complex number. And what he was working on is what happens if you want to raise it to a power. Okay, so this is what Demois came up with. He said, okay, well, what you do is you take the hypotenuse part of it and you raise that to the actual power. I shouldn't be using a 5. I should be using an n. But let me just continue with this. You raise the hypotenuse to the actual power, but the angle, you just multiply it by the power. You don't raise the angle to the power. You take that same power and you just multiply it as a regular coefficient. To do this, so this is called Demois' theorem, which I wrote on the other page, but that seems like a long time ago, doesn't it? He said R cis theta degrees raised to the n power, generic, not the 5, equals R to the n cis 5 theta degrees, okay? So this allows us very quickly to raise our complex numbers expressed in polar form. We can quickly raise them to a power with two really simple calculations. See what I mean about the math being easy, but the ideas being kind of wonky? Why would we want to take a complex number expressed in a rectangular form and raise it to a power? Why would we want to? Well, I don't have an answer to that question for you today, you guys. I'm just going to say it's a fairly easy thing to do. So that is Demoivre's theorem, and let's practice using it in a couple quick examples. 79.1. Find and there's the 5. Okay, so we've got a polar coordinate of a complex number. I'm not going to let that cis thing freak me out. It's fine. It's just another way to write a polar coordinate. And we want to raise it to the 5th power. Okay, so I'm just going to apply his theorem right here. So it's going to be 2 to the 5th cis 5 times 30 degrees. What is 2 to the 5th? Okay, let's start doubling. 2, 4, 8, 16, 32. And then 5 times 30 is 150 degrees. That's our final answer. As you may remember when we did this back in, what lesson was it? Lesson 64, when we first started playing with polar form of a complex number, we learned that if this number goes over 360, we go ahead and adjust it down by subtracting 360 to get the original spin on that. But this one didn't require us to do that. Okay, example 79.2. It says use Demoivre's theorem to find 1 plus I to the 13th. What? What in the world? What are we even doing here, right? First of all, the 13th, that's scary, but look, our numbers are really simple, so don't worry about that. Now, the problem is that John gave us this complex number in rectangular coordinates, and Demoivre's theorem only works if we're in polar coordinates. So we have to shift this into polar coordinate form, which we don't let freak us out because it's the same as our regular polar form. So we're going to draw the triangle, and we're going to find the polar coordinates. Then we're going to raise those to the 13th power, all right? So 1 plus I, I'm going to put a positive 1 right there. That tells me I need positive 1 on the x-axis, positive 1 on the y-axis. So it's going to be like this, right? This is 1, and this is 1. My point is here. Here's my triangle. That's 1 also, right? It's 1 here, and it's 1 here. Okay, so this tells me it's the right one. Now I just need to find this angle, and that would be theta, right? And then the hypotenuse is r, which is exactly what I told you way back over here, right? This number is the hypotenuse, this number is the angle. So if we get these two figured out, which shouldn't be a big deal, we can quickly get into this form, and then we'll be able to raise it to the bazillionth power or whatever it is that John wants. Okay, we know how to do this. We know how to go from polar to rectangular, or I'm sorry, we want to go the other way. We want to go from rectangular to polar. So first we have to find this hypotenuse. So that's pretty easy because we can use Pythagorean, right? It'll be the square root, this I can say equals. It's 1 squared plus 1 squared, take the square root, right? So that equals square root of 2. So r equals the square root of 2. Cool. That looks good, right? Then we need to find this angle, right? Well, this looks really familiar. We know what this triangle is because sine and cosine are the same. We know that's a 45, 45, 90 triangle, isn't it? So theta has to be 45 degrees. Okay, and we could have figured it out if we didn't know right away. We could have figured that the tangent of this thing was 1 over 1. It equals 1, opposite over, or tangent, I'm sorry. We know the tangent of theta equals 1 over 1, and that's over Arthur, right? Right, over Arthur. And we could have, well, it would have worked if we would have used our unit circle creatively. Here's our 45-degree angle, and we see that if we put the opposite over the adjacent, we would get 1, right? Because they're the same. That's the interesting thing about the 45-45 triangles, that sine and cosine are the same. So that was a hint to us also, if that was a 45-45 90 triangle. So now we have the two pieces of information we need, and we can rewrite this, or it's here, right? So 1 plus I as a rectangular coordinate equals square root of 2 cis 45 degrees. Aha! We're not quite done. We still have to apply de Moivre's theorem, but we have translated from rectangular to polar coordinates. And so now I'm going to take this to my next page. And I'm going to write our friend's theorem up here. R cis theta to the power of n equals r to the n cis 5 times theta. All right, so now we're going to take this specific number and we're going to apply this wacky rule to it. So it's going to be square root of 2 to the 5th power cis 5 times 45 degrees. All right, now here we have a little drama because look what we're doing. We've got an exponent and we've also got a pig house. So let's rewrite this square root sign as 1/2, right? Remember how we did that back in the day? It'll be 2 to the 1/2 raised to the 5th. So this will be 2 to the wait, what am I doing? It's to the 13th. I made up that thing about the 5th, right? We're raising this. I was using the exponent from the last problem. We're actually raising this problem to the 13th. So the way I handled the 2 was fine. I just need to make this number 13. Does that make sense? I hope so. Okay. And then this isn't 5. It's 13, right? Because we're supposed to be raising this to the 13th power. My bad. Sometimes my brain just gets a little too excited and I mess up the easy parts. All right, so now this 2 to the 13 over 2, how can we simplify that? Well, we can see it as 2 to the 12 over 2 times 2 to the 1 over 2, right? Because the product rule tells us that if we're multiplying the bases, then we add the exponents. And so 12 over 2 plus 1 over 2 would get us to 13 over 2. This will leave just like that. 12 over 2 is equal to 6. So now we need 2 to the 6th power. All right, I like to do this on my hands. 2, 4, 8, 16, 32, 64. So our coefficient, or not our coefficient, our hypotenuse is 64. That's correct. Okay. But we also have this left. So I have to do times the square root of 2, right? I'm going to put that back into the radical form because I got that part separated. That's why I wanted them in fractions. Now we can leave it like this. Make sense? I hope so. Please say yes. Okay, so that was all just to figure out. This side was the hypotenuse, right? So this is the new hypotenuse of our polar coordinate of this raised to the 13th power. Now we have to deal with this, okay? So we know for this one, we just take 45 and we multiply it by 13. 5, 135, and then this would be what did I do? Oh, I see. Oh my gosh, you guys, I'm having trouble with the easy parts. 45 times 13. If only your math teacher knew how to multiply. 5, 13, 45, like that. I scooched it over too far. 5, 8, 5. Okay, so that tells us that this is 585 degrees, right? That is our angle. But we can see that it's over 360, and we know that we don't want to have hyper rotations like that. So we're going to subtract 360. 5, 2, 2. So this is the angle part of it, right? Okay. So what we have here is the polar form of this complex number raised to the 13th power. However, John also says express the answer in rectangular format. Lord have mercy. But, here comes the good part, you guys. Because this form tells us that it's 64 square root of 2 times the cosine plus I times the sine of 225 degrees, and this is also 225 degrees. I always go back and fill that in later when I remember, oh yeah, the angle relates to both, okay? So what that means is that we can take our super cute and ever so groovy unit circle and go, okay, well, what is the cosine of 225 degrees? Here's 225 degrees. Cosine is the first number. It's minus square root of 2 over 2. So now I'm going to take all of this and I'm going to say it's 64 square root of 2 times minus square root of 2 over 2. I pull the cosine value for 225 degrees right off my unit circle. I drop it in. That's how this CIS thing becomes super helpful. Okay? And then to find the sine part of it, so it's going to be plus, maybe it'll be a minus sign, but we'll start with a plus. Then we take 64 times the square root of 2 times the sine of minus 225. Oh, look, it's the very same. Minus square root of 2 over 2. This would be helpful if it had bigger, because we're basically distributing this angle measurement across both of the trig values. This is a better way to write that. Okay? And then this is the I component, and I'm running out of space here, but we'll associate I with this half, right? I goes with the sine because the sine relates to the y-axis, and that's where we put the complex number. So now all we have to do is simplify. Square root of 2 times square root of 2 makes a positive 2, and it cancels against the denominator. So this is minus 64. And then over here, we have another minus sign. So this plus will switch to a minus, and the numbers will do the same thing. Square root of 2 times square root of 2 is positive 2. That cancels against the denominator. And we get 64 minus 64i as our final answer. Whoa, that was kind of a lot, wasn't it? But kind of satisfying that we're able to take this and raise it to the 13th power and get actually a fairly cute answer, wasn't it? Okay, now here what we did was we took complex numbers and raised them to a power. Now we're going to flip it, and we're going to take the number that is a power, a bigger number, and we're going to learn how to find the roots of it. Okay, so now we're working in the opposite order. Okay. So this is part B, and it's called Roots of Complex Numbers. I wish the other one would have been called Powers of Complex Numbers. That would be a better name because roots and powers we know go together. All right. Find the 4 fourth roots of 16 cis 60. Okay, well, we already know, don't worry too much about this 4. We'll get to that. We're trying to find the 4th root of that. Okay, well, we know how to make a power, so if we want to find the root, we'll just work backwards, right? So what we'll do is we'll take, in this case, we're finding the 4th root, right? So we'll take the 4th root of this number, and then we'll divide that number by 4, right? That would be the opposite of Demoivre's theorem. We're kind of working it backwards, right? So we know that the first of the 4 fourth roots, we use Demoivre in reverse, right? So for the hypotenuse number, we take the 4th root of it, so that would be 2, right? 2, 4, 8, 16. Yes, so that is 2. And then for this number, we divide it by 4. So that would be 15, right? So this is the first of the 4 roots. Okay? That one is not too bad. That one's pretty easy, right? We just move that one. We work backwards using what we already learned from our little friend Demoivre. Okay, now, here's the thing. Whenever we find a root, there's more than just one answer. There's usually one real number answer, but there are complex numbers as answers too. So that's what we're finding now. And that's a little weird because we're used to not having all of these roots. But just play along and pretend it's fine. Here's the way we find, in this case, the 2nd, 3rd, and 4th, the additional roots. So I'll write this as a general rule. We take 360 and divide it by the number of roots we're finding. So in this example, it would be 360 over 4 because we're looking for 4th roots. Okay, that number is 120. Then what we do is take this number and add to the angle. All right, so our 2nd root will be 2 cis. Oh, just a second. I am sorry, you guys. That is ridiculous. What am I? You must just be sitting there going, what is she talking about? 90, not 120. I have no explanation. I take this number and I add it to my other angle. This 2nd root is 105. The 3rd root is 195. And the 4th root is 285. Okay? Oh my goodness, what a crazy lady I am tonight. And I'm just double checking to make sure I got all these right. 105, 195, 285. Notice that if we added one more 90, we would be at 375, and that would be over 360. So this little calculation allows us to add just the right number of roots. Okay, so this we call the first root, and then this is the second, the third, and the fourth root. Now, the last step in this is John wants us to check our answers. What? What in the world? By the way, this is problem 79.3. Check our answers. Okay, well, that's fine. We're just going to use Demois' theorem to boost it back up. So let's take, so here we're going to do check. Let's start with this one. 2 cis 15 degrees, and we want to raise it to the fourth power, right? Okay, well, that means 2 to the fourth is 16, and 4 times 15 is 60 degrees. Okay, check. That one works, right? How about the next one? That was 105. And that's to the fourth. Well, the 16 works. And now 4, remember, not as an exponent, but 4 times 105 would be 420. And then we would subtract 360 from that, and we would get 60 degrees. That works perfectly. Now the third solution, 195 to the fourth power. Again, the 16 is working the same every time. 195 times 4. Lord help me, I'll probably destroy this one too. This is almost 200. So if it was 4 times, remember, even though it's an exponent here, we're not using it as an exponent. We're using Demois. There's not a plus sign there. Right? We take the exponent down and we multiply it by the angle. So we're multiplying 195 times 4. It would be 800 minus 20. It must be 780. And then we can subtract 2 rounds, right? 360 and 360 are 720. And look, there's our 60 degrees again. And now the last one, 2 says 285 to the fourth. Again, we take the 2 and we raise it to the fourth power. That's 16. This one, we don't raise it to the power. We multiply it. 285 times 4. I don't think I should even try, you guys. I don't think I should even try. Let me get a scrap paper here. It's not scrap paper. It's just so I don't have to turn the page. I shouldn't say scrap paper. 285 times 4. 0, 2. 32 plus 2 is 34. 8, 10. 1040 is our angle measurement. And now we need to subtract, let's see. 2 360s is 720. Did I do this wrong? Oh, it's 11. Yes, this I carried a 3. Oh, I did screw up that multiplication, right? 4 times 5 is 20. 2. 4 times 8 is 32. 34. That's a 3. That's 8 plus 3 more is 11. Okay, so it's 1140. Now I feel better because this adds to 1080, right? This is 360 times 3. So when I subtract that 1080, I'll get my 60 degrees again. And that is what I want there. So all of these other solutions check out. Okay? So we can check and prove that this delightful little process works. Okay, now, in this problem, John told us to find these roots, but he gave us our number in polar coordinates. What happens if he's mean? I mean, John's never mean, but on the other hand, he's always mean. Find the 5/5 roots of I. What? That's not a polar form of a complex number. That's a freaking letter. What is even that? Well, what we have to recognize, and granted, this is a leap, we have to recognize that this is actually a rectangular coordinate of 0 plus 1i. Right? There's no real number component, so we put 0 in, and then we can put a 1 in for that. Okay, that's crazy. So let's take a look at what that would look like graphing. Well, it's 0 on the x-axis and 1 on the y, which we call the I, right? The y is the I. Okay, so it's this triangle. Oh, well that is a 90-degree angle, right? That's pretty easy. So it's 1 is the hypotenuse, and the angle is 90 degrees. Okay, so that is the way that we change that to the polar form. Okay, and this was the rectangular form. Okay, this was rectangular, but it just looked so freakish that we couldn't even wrap our minds around it. We filled in the blanks. That's still rectangular. Then we drew it and realized, oh, that's easy. That's just a 90-degree angle with a hypotenuse, if you will, of 1. It's a quadrantal angle, isn't it? Okay, cool. So now what we want to do is we want to find the 5/5 roots of it, right? So what that means is we will take, to find the first root, we'll take 1 to the 1/5, the fifth root of it, and then we'll take 90 divided by 5. Well, the roots of 1 are really easy. They're just 1, and then 90 divided by 5 is going to be 18, if I haven't lost my mind. It is 18. So there is our first root. Okay? Take the root of the hypotenuse and divide the angle by that number. Okay, now what about the additional roots? Okay, we take 360 and we divide it by 5, and that equals 72. 72. So we'll be adding 72 degrees to this each time we bump up. The hypotenuse stays the same, we just keep bumping up the angle. So our additional roots will be 1. Let's see, 72 plus that would be 90 degrees. And then we add it again, that would be 162 degrees. And then we're up to what, 235? No, 234. And one more time, it will be 306. 306. It's not an O, it's a 0. Okay, so these are the 5/5 roots of this original complex number. Now, it takes a fair amount, and this is the part that I was talking about at the beginning of the lesson. It takes a fair amount of imagination to imagine it's a complex number and we're taking roots of it. What? What does that even mean? And how come we're using triangles to find the values of these? It's a little theoretical and it's a little abstract for us. What I mostly want to emphasize to you is that even though we're talking about complex numbers and doing these weird calculations, we're just using our basic tools of trig to manipulate these numbers, either multiplying them up to raise them to a power or finding the roots of them once we get them so big. Here are the 5/5 roots of this crazy number. Okay, right? Don't ask me to really explain it in practical terms. Don't ask me to make up a word problem that gives you a context for this. I can't do it, but I can say, yeah, that's the calculation, right? It's not too bad. Okay, we're not going to check those. John does not ask you to check them. Example 79.4. Find 2 square roots of 1. Okay, well, it seems like it should be pretty easy, but let's use our process, right? Okay, square roots, that means 2. This is not in the proper form, so let's see how would we do that. It would be 1 plus 0i this time, right? Because we don't have an imaginary component. Okay, and let's draw a picture of what that would look like. Okay, it would be right here, right? Because it's 1 on the real number axis and 0 up. So that would be hypotenuse of 1 at 0 degrees. That's our first number. Okay, that is that. The square root of 1 is 1. We know that the 2 square roots of 1 are 1 and -1, right? We know that inherently, that the answer must be that. This is the polar way of saying the number 1, right? Because that's 1. Now what we have to do is find a way to say -1, right? We know those are the 2 answers. They have to be. But now what we want to do is find the polar form of the second value and see if there's any way that makes sense. Okay, so this is our first root. And we know for the additional roots, there's only going to be 1 this time. We take 360 and we divide it by the number of roots 2. That equals 180. So then we add that to the angle part to get the second root. And let's draw a picture of what this, because we know this has to be -1, right? Okay, what happens if we draw 1 unit out from a 180-degree angle? Look, it's right here. It's right here. It's -1. So this problem to me is very satisfying because I can actually make sense of it. The square root of 1, we know it's 1 or -1. That's logical, we understand that. And what we realize is this is just another way of writing 1 and -1 using polar coordinates. So this one I really like because it kind of sort of makes sense. This was 79.5, sorry. Oh, now I can't even write the numbers of the problem down. You guys, I don't know what to say to you. I am very sorry. I'm a little loopy, but I mean, I'm getting the hard part right. It's the easy part that I can't manage. Okay, one more. Example 79.6. Find 3 third roots I usually just write down what root they want because I know it's the same number. We always find the same number as we are taking roots of -1. Okay, that doesn't look like a polar coordinate. So first, it doesn't look like a rectangular coordinate either. So first, let's turn it into a rectangular coordinate. It would be 0. It would be -1 plus 0i. I should write this just to remind you. That's the form we need the rectangular number to have. All right, -1 plus 0i. Let's take a look at that. Oh, we just did that, didn't we? So it's -1 on the x-axis and 0 on the y-axis. So it's right here, right? And so that would be a 180-degree angle. So our first it would be 1 cis 180 degrees. That's our first. And we see it right here. That's 180 degrees, and we're 1 unit out, so that's at -1. Now, again, for our additional roots, we take 360 and we divide it by the number of roots we're dealing with. That is, please help me, 120. Whew, I managed to get it right. So now we start adding oh, I see the mistake I made. This is not correct. This is the rectangular form. This is the polar form. 1 cis 180 degrees. Now we have to take the first root of it. I skipped that step. The first root of it is to take the cube root of 1, right? It would be the cube root of 1, and this would be 180 over 3. I forgot to take the root. I just started with the polar coordinate and was adjusting from there. Okay, the cube root of 1 is 160 degrees. That's the first root. Does that make sense? I skipped this step of finding the first root. I just went straight. I took my polar coordinate and I used that as if it were the first root, but that's not right. This is correct. For the additional roots, we do 360 divided by 3 because we're finding third roots. That's 120, so it will be 1 cis 180 and 1 cis 300 degrees. Does John agree with me? Oh, praise the Lord, he does. Goodness. Okay, that is the last lesson. Remember, what we were doing is we were raising complex numbers to higher powers. We were raising them up using our friend Demois' theorem. And then we went in the other direction and we were taking complex numbers, sometimes already written in polar form, and we were finding the roots of them. But we also were getting thrown curveballs where John would throw us a rectangular number. Then we'd have to turn it into a better rectangular number, and then we'd have to convert it to a polar form, and then we'd have to take the roots of that, right? Whew. Okay, I hope that made sense to you. Lesson 79. Thank you. Goodbye.